What if you could calculate the area of a triangle on a grid or the volume of a pyramid in space using much simpler expressions? That's exactly what linear algebra lets us do. Instead of this, you can do this. Instead of this, you can do this. These formulas can become building blocks for computing the area or volume of more complex figures, like 3D computer models made from webs of triangular polygons. But what we'll ultimately develop in this video is a powerful idea called the determinant, a value that not only helps us measure area and volume, but also determines whether a matrix is invertible. Let's say we want to find the area of an irregular shape, like this lake. There are many approaches. One idea from calculus is to approximate the lake's boundary as a function and integrate between curves. But real-world shapes aren't nice. They're jagged and bendy and definitely not functions of x. We could instead overlay a grid of squares and count them to approximate the area, but squares are inefficient for curved edges and you need a lot of them. A better idea is to use triangles. Place points strategically around the boundary, connect them into a web of triangles, and sum the area of each triangle. That uses much fewer shapes and is a better fit. We can use a similar strategy to find the volume of 3D objects, especially 3D computer models, which are already stored as a web of coordinate points. We can start cutting off pieces in the form of pyramids and calculate the volume of each pyramid and sum them all up to find the volume. But these strategies will only work well in practice if we have an easy way to find the areas of these triangles and the volumes of these pyramids from coordinates of vertices. Surprisingly, there are simple formulas for both when we move from coordinates to vectors. Let's start with areas. Using the standard equation for the area of a triangle, how would you find the area of the triangle given these 3 points as the vertices? We'd need to find the length of the base and a height, which will take some work using the Pythagorean theorem and a trig function. Honestly, counting squares seems much easier at this point. But there's another strategy. We can put a rectangle around the triangle by projecting the vectors to the axes so we have right triangles to work with. We calculate the area of the rectangle and subtract off the area of these 3 triangles. These 3 are easy to calculate since they are right triangles oriented with the grid. Still looks a little crazy with all those differences for lengths though. We can simplify many of the differences. The vertices are actually giving us more information than we need. The vertices together tell us the location of the triangle, but the area won't change if we move the triangle somewhere else on the grid. So let's move it so one of the vertices is at the origin. What we've done by translating the triangle with a vertex at the origin is simplified the inputs to the problem. Instead of 3 points, we now just have 2 vectors. Using the 2 vectors simplifies the math. So much so that we can use the power of algebra to derive quite a simple formula for the area of the triangle given 2 vectors of sides with tails at the same vertex. It isn't quite as simple as base times height divided by 2, but it is much nicer if we don't already know the base and height. Let's call our vectors a, b, and cd, and using the same rectangle approach as before, that would make this side d, this side a, while the top side is c plus a minus c, and the right side b plus d minus b. Now all these crazy differences look like this, and we can simplify to find the area of the triangle. Technically this expression could be negative, so the area is the absolute value of this expression. But this expression does more than tell us the area of a triangle. It turns out that the numerator in this formula, AD minus BC, is so valuable in mathematics that it's given a special name. It is called the determinant. You likely won't find this connection to triangles though in most textbooks. Most formulas for the 2 by 2 determinant lack the division by 2, so they don't link it directly to the area of a triangle. Instead, they connect it to the area of a parallelogram, which is made up of 2 congruent triangles. The derivation for the area of the parallelogram is actually pretty slick. A quick way to remember the formula is to multiply the 2 values in this downward diagonal and subtract the product of this upward diagonal. It was named the determinant because it helps us determine if a square matrix is invertible or not. But how? Well, knowing now how the determinant formula is connected to areas of triangles and parallelograms, it actually makes a lot of sense. Remember in this previous video we learned that for a square matrix to be invertible, its column vectors must be linearly independent, meaning no vector can be written as a linear combination of the others. If they could, they would look like this, and that would be the area of a triangle formed by these 2 vectors, which is 0. So if the determinant is 0, then the area of the triangle is 0, which means the vectors are not linearly independent, thus the matrix is not invertible. We can also see this connection algebraically from the formula for the inverse of a 2 by 2 matrix. Notice that in this formula for the inverse, the matrix will always have an inverse except when the determinant is 0. since the division out front would now be undefined. Determinants are also connected to the transformation of a matrix. In 2 dimensions, the area of an image in the plane will be scaled by the absolute value of the determinant of the matrix after applying the transformation. If the determinant of the transformation is negative, that means the image changes orientation. But remember, in mathematics, orientation means something a little different than everyday language. In everyday use, we often use orientation to refer to the direction an object is facing. However, in mathematics, it refers to a change in an object that's captured by a kind of reversing. For example, if going around the vertices of a polygon in order is in a clockwise direction, and then going around the transformed vertices in the same order travels in a counterclockwise direction, then there was a change in orientation. In a plane, that means there was a reflection as part of the transformation. Now we can more easily make sense of why we divide by the determinant in the 2x2 inverse formula. If multiplication by the matrix scaled an image by the determinant, then to reverse the transformation, we need to scale the transformed image 1 over the determinant to restore the image to the same size. And if the determinant is negative, then there was a reflection as part of the transformation, and we need to multiply or divide by a -1 in the inverse transformation to reflect it again to restore the original orientation. Even if a determinant is 0, it tells us something about the transformation. A 2x2 matrix with a 0 determinant means that it transforms images with positive areas to images with no area. In other words, it collapses the image, and actually the entire plane, down to a line or a point, both of which have 0 area. Mathematicians have a special notation for the determinant of a square matrix: straight lines, like absolute value lines, in the sides of the matrix instead of the square brackets. It is important to remember that this is a single number. It's the determinant of the matrix. The determinant even generalizes to higher dimensions, although the formulas get more complex. When trying to find the volume of a pyramid in 3 dimensions, given coordinates of the vertices, we can do a similar strategy that we did with the triangle, by translating one of the vertices to the origin, or equivalently thinking about vectors as the change in position from one vertex. We can do a similar strategy to our area case, but instead of making right triangles with sides on the coordinate axes, we make pyramids with faces on one of the coordinate planes, then subtract off some pyramids and add in others. With a face completely in a coordinate plane, then the volume calculation is straightforward, since the height is given by one of the coordinates of a vector, and the area of the base is easily calculated with our 2D area formula. Now we plug in that information to the volume formula for a pyramid, and here we have it. When no faces are in coordinate planes, we can project faces onto one coordinate plane to make 3 different pyramids with easy to calculate volumes, and find the volume by adding 2 and subtracting 1, but we won't go into all of the details here. We end up with this formula for the volume of the pyramid, which simplifies to this. The numerator is the determinant of a 3x3 matrix. It represents the volume of a parallelepiped defined by the 3 vectors. If we only care about the determinant and not the volume of the pyramid, the form is equivalent to what many of you learned in your linear algebra class: calculating the determinant by expanding along a row or column. Since it doesn't matter which coordinate plane we project bases to for the calculation, it doesn't matter which row or column we use for the expansion. What we learned about determinants in 2 dimensions generalizes to higher dimensions. For example, the absolute value of the determinant of a matrix is the factor by which a volume is scaled when transformed by the matrix in 3D. Instead of memorizing the formula for the determinant, students are often taught this strategy involving products of 3 downward diagonals and subtracting the products of 3 upward diagonals. Unfortunately, this strategy does not generalize to 4x4 or higher matrices. You can look up other videos where it will walk you through the calculation process for those larger matrices. Luckily, putting a square matrix into Wolfram Alpha automatically gives you the determinant of the matrix. The 3 blue 1 brown channel has a really nice video on determinants. I encourage you to watch it. It has really nice animations and approaches the content from a slightly different direction. The link is here. Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.